the Large Hadron Collider. It is near Genova in Switzerland, in Central Europe, which is Southern Europe. It's operated by CERN, and it is built into the in the 80s built Large Electron Positron Collider, 100 meters underneath the ground. And it is 27 kilometers long. It is not a circle. It is an octagon, so of 8 sides. And it is the largest machine in the world, and it is cooled down to almost absolute zero, to 1.9 Kelvin. Now, and what happens there? There are strong magnets, strong electromagnetic fields who are kicking protons, one in that direction, the other one in that direction. They're kicking them always, if they pass it with one thing, they're kicking it on to the next part. One proton to that direction, other protons into that direction. And at 4 of these things, there are now other magnets, and they are trying to push them very small together. Protons are very, very, very small, on a very small places, so that actually, when at one curvature, hit exactly the other ones. And then they bang together. Now, and that works, and that the electric resistance of the magnets is not a break on them. They are super cooled down with helium, and also they are superconductors, these magnets. Now, and when they bang them together, then there are things to measure them. There's ATLAS and LHCb and CMS and ALICE. These are detectors. When they bang together, these protons, they are breaking up into gluons and quarks. And because we smash together, and inside of the protons, there are gluons and quarks. And when they are then detected, so first it goes on, there comes then concentric cylinders up in there. The first one is a semiconductor. So in that semiconductor, where the electrons very loosely bound. Semiconductor, you add just one electron, and it can conduct electricity. You take it away, and it does not conduct anymore. Now they come against it, and they are pushing basically at these loosely bound electrons in this semiconductor all them around, and you can see pretty much exactly where they were with gluons and quarks. And the next thing are the magnets, and they're pulling at them, and at the curvature it becomes clear how much they were pulled in, what the momentum of it was. Now, and then it is able to take that momentum at the next cylinder. So there's then at the next cylinder, there's now liquid argon and lead tungstate. And where these are stopped, gluons and quarks are stopped in that very solid material. And when they are decreasing in speed, these gluons and quarks, they were accelerated, these protons, to 99.9999% of light speed, of speed of light. Now, when we're decelerating these quarks and gluons, then they're emitting photons. And these photons, the momentum can be now seen and calculated back to what mass they had. And the muons, they are going through it. These detectors out of lead tungstate and liquid argon, they are detected later. And the neutrinos, they are not detected at all. But it is able to calculate back what mass they had, because from the photons, how much mass the neutrinos had. No, neutrinos not. The neutrinos, they can be, if all is calculated together, what was measured, the subtraction of the neutrinos. Now the Higgs is the thing where it is calculated back. It is not, the Higgs is decaying too fast. But it is sometimes predicted to be decaying into high energy, a high energy pair of electrons, of photons, a high energy pair of photons. And it can be calculated how much Higgs would be there. Now, and if it's sometimes decaying into these high energy pair of photons, they can again measure it with a momentum and how much energy they had, with the magnets pulling at them, changing the momentum. It can be calculated back, translated back, how much energy that Higgs had, and how much mass it had. And now the Higgs has 125 gigaelectrons. And where the Higgs was discovered with the Large Hadron Collider on the 4th July 2012. And that is the Large Hadron Collider, and that is all according to the Richard Webb's particle physics book on the page 57 and 50.